Hello, I'm Giovanni. I'm a PhD candidate at the University of São Paulo, and I'm currently doing an internship at École Normale Supérieure de Lyon in France. And I'm going to present my work entitled Spectroscopic Evidence of the adduct DBU carbon dioxide in ionic liquids, a possible new path to activate carbon dioxide through a superbase. And I would like to start explaining what's this class of compounds called superbases. Superbases are compounds showing very high basicity in organic media, which is given by its pKa values, as we can see over here. And they are usually amidine or guanidine bases, which we can see here, the amidine moiety. And so they are also called proton sponges due to its behavior. Some of them are known to bond with CO2, forming the corresponding adducts, as TBD, which is a guanidine, and DBN, which is very similar to DBU. The adduct with TBD was first obtained in 2010 in organic solvent THF. The adduct with DBN was first obtained in 2011 in its solid form, and the adduct with DBU was not obtained yet, so we're aiming to verify if we can obtain it in ionic liquid medium. So the objectives of this work are to verify if the adduct DBU carbon dioxide can be identified in two ionic liquids from the same anion. Ionic liquids are simply liquid salts. So we tested these two ionic liquids, imine TFSI and BTMA TFSI, and also to characterize the systems through spectroscopic techniques as infrared, Raman, and NMR with the support of density functional theory calculations. Experimentally, we prepared the DBU solutions in these two ionic liquids at 10 to 1 molar ratio, ionic liquid to DBU, under a nitrogen or argon atmosphere. And then we saturated these DBU solutions with ultra-pure CO2 under ambient conditions. And after this, we characterized these systems through Raman and infrared spectroscopies, NMR, and also gas absorption capacity measurements. In the theoretical part, we calculated the adduct at this level of theory in different solvents as eptane, DMSO, and the ionic liquid in order to obtain energies and predict Raman and infrared spectra to help in the assignment of bands. In the Raman and infrared spectrum recorded before and after carbon dioxide absorption, we could notice in the infrared spectrum the emergence of the band assigned to the asymmetrical stretching of carbon dioxide, which means that CO2 was chemically absorbed. And in order to get some clue about which species is being formed, we could analyze the band assigned to the carbon-nitrogen stretching, which here at the Raman spectrum, we can see that after the carbon dioxide absorption, the band is no longer there. However, in the infrared spectrum, we could notice that the band is still there and shows two components after the absorption of carbon dioxide. So in order to get an insight on it, we can compare the DFT results of these three structures calculated, which is DBU and its two possible products after the absorption of carbon dioxide. And if we compare the carbon-nitrogen bond lengths, we can see that no matter if a hydrogen or carbon dioxide is bonded to DBU, these two bonds become equal in length. So this means that this single stretching carbon-nitrogen, if a hydrogen or CO2 is bonded to it, become two different stretches, which is the carbon-nitrogen symmetrical and carbon-nitrogen asymmetrical stretching, which are only active in the infrared spectrum as we saw in these two components. So we still don't know if it's carbon dioxide or hydrogen bonded to DBU. And then only carbon NMR was capable of identifying the species being formed. For it, we had to add labeled carbon dioxide to see the enhancement of the peak of the main species, which we could assign to the CO2 bonded to DBU, the signal at 160.4 ppm. And also we could identify the other peaks assigned to subproducts. We could also unveil that the ionic liquid is responsible for stabilizing the adduct, since the more diluted DBU is, the more CO2 it absorbs. And also DFT results points to an stabilization effect from the ionic liquid, since CO2 is closer to DBU, CO2 is more banded, and it interacts stronger in the ionic liquid than in the other solvents. So we can conclude that the adduct DBU carbon dioxide is obtained in the two studied ionic liquids. We can also conclude that there is an additional mechanism of absorption that produces another subproducts that we could evidence through NMR in the imine ionic liquid. And also, that the ionic liquid plays an important role in stabilizing the DBU carbon dioxide adduct. Thank you very much for your attention, and I would like to thank as well the institutions and the labs in which I'm working, and also the Brazilian agencies that are funding this work.